In this video, we'll be talking about rational functions and rational equations. Let's start with the functions. A rational function is a function that is written as a fraction. It's a function that divides two polynomials. So think of p of x like a polynomial and q of x like a polynomial. We're just going to divide these two polynomials, and that's what puts this into this category, this rational function category. Anytime we start to form a fraction, mathematicians always worry about being able to divide by the denominator, and so we always put in the little caveat, and I must have left it out here, that q of x cannot equal 0. Okay, so I can't divide by 0, so I don't want to allow the denominator to be 0. That actually plays a part in the domain. Remember, the domain is the set of all the x values that work for this function. So I can pretty much use any x values I want, but I want to make sure that the denominator does not turn out to be 0. And that's really true for any function that's a fraction. So to find the x values that don't work, I'm going to set the denominator equal to 0, and I'm going to solve for x. And then I'm going to exclude these, right? I'm going to leave them out, and I'm going to describe the set of all the other x values except this one. Okay, so let's try that out. We're going to start with the most basic rational function, which is y equals 1 over x. So what x value can I not have? Let's do it like this. So I don't want the denominator to be 0. In the bottom here, I just have x. So really what that means is I don't want x itself to be 0. For other functions, it might look different, but right now 0 is the number I don't want to allow x to be. I really want to write this in interval notation. We've done this before, but it's been a little while since we've talked about it. So let me draw my number line picture. Remember, the number line is just a visual aid, and it's not the final answer. So I want to leave out the number 0, so I'm going to draw in an open circle. But I want to include all the negatives are fine to plug in, and all the positives are fine to plug into my function. Just not 0. So my domain, I'm going to list it in interval notation from left to right. So I'm going to start at negative infinity all the way up to 0, but I don't want to include 0, so I'm going to go all the way up to just before 0. But I'm still going to write the 0 here. I use the parentheses to show that I'm stopping just short of 0. And then on the right-hand side, I'm going to pick up just after 0, infinitely close to 0, and then go all the way on the right to infinity. Anytime I break up the interval notation into more than one part, I'm going to put the union in the middle. All right, so that's my domain. We're not really going to talk about range for these functions, although we could. We're really just going to focus on the domain part. Okay, so now let's make a graph of this function. The graph for a rational function has a very special kind of look to it. Notice that the domain is broken up into two parts. So actually the graph is going to be broken up into two parts because I have this number in the center where it's undefined or it doesn't work. Okay, so I always put that number in the middle of my t-chart. So at 0, it doesn't work, so it's undefined. We usually draw in a special line just to make sure that you can see it. I'm going to draw it with a highlighter, but you could just draw it with a regular pencil if you wanted to. But we draw in a dotted line. It's a line. The line is not actually part of the graph. It's just kind of a guiding line. Because the actual graph is going to get infinitely close to this line, but never touch it. It can't touch it because we can't divide by 0. right? And if we did touch it, we would have to plug in x to be 0, and we can't do that. Okay, since it's dividing the graph into two parts, I want to make sure I pick points on both sides of 0. So I'm going to pick a couple numbers smaller than 0, and I'm going to pick a couple numbers larger than 0, and I'm going to plug those into my function. So I'll have 1 over -2. That'll be -1/2 or -0.5 if you like that better. 1 over -1. 1 over 1. And then 1 over 2. Okay, so let's plot those. So at -2, I'm at -1/2. At -1, I'm at -1. We could definitely pick more points. If I were to do, say, -3, I'd be at -1/3. -4, I'd be at -1/4, right? And likewise, if I chose some more points kind of in between -1 and 0, like -1/2, I would get -2. And -1/3, I'd get -3. So this curve is going to hug, it actually hugs both the x-axis and the y-axis. All right, so those were the negatives, right? This was the left-hand side. Now I want to do the same thing on the right. It's a similar curve, but it's in a different place. So now I have both positives, right? So 1, 1, it's going to be in this first quadrant now. 2/2. Okay, and that's all the points we've listed here, but we could pick more. If we did pick 3, it would be 1/3. 4 would be 1/4. If I put, again, something between 0 and 1, like 1/2, 1 divided by 1/2 would be 2. Right, so it's going to have that same pattern. Sometimes we say for this relationship, x and y are inversely proportional, which means as x gets really big, the y value gets really small, almost to 0, but not touching it. And as x gets really small, either on the positive side or on the negative side, y gets really big, either really big positive number or a really big negative number. Okay, and notice that the dotted line we drew shows the separation, right, between the one side and the other side. Okay, so I am going to be very loose in how I look at your graphs for this. We're going to spend a lot of time in college algebra nailing down all the specifics. For us, I want to make sure you draw in the vertical asymptote as a dotted line. And then you should have a couple points on both sides, right? I would like your curve to look pretty much like this one, but if it's a little wonky, I'm not going to judge, okay? All right, let's try one more. How about y equals 1 over x plus 2? Okay, and we'll kind of ask the same questions. So what x value can we not have? Remember, I don't want the denominator to be 0. So there's a couple of ways you could work that out. One way is to just kind of isolate the denominator and say, hey, I don't want it to be 0. We've done this before at the very beginning of the semester, but it's been a while. We could solve, right? And that's going to tell me, okay, -2 is the number I don't want. Why is -2 a problem? Because if I were to plug in -2, I'm going to get 1 divided by 0, and that's not okay. I can't calculate that, right? So for that reason, I want to leave -2 out of the domain. If you need to, draw a picture. Now it's -2, sorry, that we want to leave out. So we'll draw an open circle. Anything smaller than -2 is okay. Anything bigger than -2 is okay as an x value. We just can't use that one number, -2. So our domain is going to go from -infinity up to -2. We're not including -2, so we're using the round parentheses. And then we're going to pick up again just after -2, so another round parentheses up to infinity. To make the graph, just like before, we're going to put that number that doesn't work, because that's the number that's dividing the graph into two parts. We're going to put that in the middle of our t-chart. Just like we showed right here, I can't use -2. 1 divided by 0 is undefined. It doesn't work. Okay, so that's where our vertical asymptote is going to be, that dotted line that's going to break up the graph. It's going to be right here at -2. And just like the last one, we're going to pick a couple points on either side so that we make sure we get the two pieces of the graph. So a couple numbers smaller and a couple numbers larger. And then I'm going to take these and plug them in. Don't forget the 1 over. Everybody forgets that. Don't do it, okay? I'm going to plug in -4. -4 plus 2 is -2, but it's 1 over -2, right? Or -1/2. -3 plus 2 is -1. 1 divided by -1 is still -1. If I plug in -1, I'm going to have 1 divided by 1. If I plug in 0, I'm going to have 1 divided by 2. Okay, we're going to stick with some really basic functions. So I would say probably the most of the time your y values are going to look pretty much the same. Right? Notice these are the same y values we got for the last example. This one's the same shape. It's just that we shifted it over by 2. Okay, so we have -4, -1/2. -3, -1. Again, we could pick more points. But we know it's going to approach this dotted line in the middle, have a curve sort of like that. On the other side, we have -1, 1, and 0.5. Same thing, right? I could pick more points, but I know it's going to hug the dotted line. And for most of our graphs, it's also going to hug this x-axis. All right, I hope that gives you a good idea about the graphing portion. Now let's check out how to solve an equation. Okay, so for a rational equation, that's going to be an equation that has a fraction in it with variables. Just like we said before, the solutions cannot make the denominator 0. So I usually jot down what number would make the denominator 0 off to the side. And when I'm done with my problem, I need to just double check that I didn't get that number because it's not going to work. Okay, and then here's the strategy we're going to use. We're going to factor the denominator if we can. And then we're going to multiply both sides of the equation by the least common denominator. We've done this before when we didn't have variables, but now we have variables, but it's the same strategy. We're going to multiply it so that we can get rid of the fractions and then solve it as we normally would, right, in previous chapters. Okay, so let's try a couple of these. Here's the first one. First of all, I call these the restrictions, right? What number can x not be? What number, if I were to plug it in right here, would make this whole denominator 0? That's -3, right? Because -3 plus 3 would make 0. So I don't want that number. I need to make sure I don't get that number because it's definitely not going to work. All right, and then I want to multiply by the least common denominator. In this case, I only have one denominator, so I'm going to multiply both sides by x plus 3. Okay, so let's do that. So I'll have x plus 3. I'm going to multiply by that on the left. And on the right. The whole point of doing that is to remove the denominator. So x plus 3 divided by x plus 3 is 1. So these cancel. I'm left with 3x. I'm going to go ahead and distribute my negative 6. Okay, so now I have an equation. I don't have any fractions anymore, and this is something I'm pretty comfortable with solving. That's the kind of the whole point of that strategy. So now I want to finish solving. So to finish solving, I'm going to get all my variables together, kind of do my normal thing. I'm going to divide by 9 on both sides. And I'm going to come over here. That's going to give me x equals negative 2. Okay, I don't have to do a formal check here. All I do have to do is just kind of a quick check. Notice I did not get negative 3, so I'm good. If I had gotten negative 3, that would not be a valid answer. So think of these as all the candidates, right? Any numbers I get here at the end are my candidates. If they're on this list, they don't work. So if I had gotten negative 3 here and I knew it didn't work, my answer then would be no solution. But that didn't happen this time, so I'm good. All right, that's the basic idea. I just brought several different types of examples just to show you all the different variations you might see. But really, this is the basic idea. All right, there are problems in 2 sections of your textbook like this, 6.1, which is where this one is from, and 6.4. So I'm going to do problems from both. They look a little bit different, but the strategy is the same, so I figure we may as well look at them at the same time. All right, so let's look at this one. First of all, what x value is not going to work? Negative 1, right? Because negative 1 plus 1 would make 0. Okay, and then notice here my denominators are the same. So I'm going to multiply all the parts here by x plus 1. All right, so let's do that. So this problem has actually 3 parts. This fraction, this 1, and then this fraction. So when I multiply, I have to multiply everything so that I don't change the equation. And that includes the 1 there kind of in the middle. So I'm going to multiply this fraction. I'm going to multiply the 1. It's really easy to forget the numbers that are not fractions, but they still need to be multiplied. So try not to leave those out, or it will definitely throw off your answer. All right, remember the whole point of this strategy is to remove the fractions. So x plus 1 divided by x plus 1 is 1, and times 1 is 1. Let's go ahead and distribute this. So that'll be minus x minus 1. Same thing here. These are going to cancel and leave us with 3. All right, so again, the fractions now are gone, and we're left with something that we're pretty comfortable with canceling. This is a positive 1, and this is a negative 1. So these are going to add to 0. This is like negative 1x. So I'm going to divide both sides by negative 1. Again, I don't have to do a full-blown check. I just have to do a quick check that I didn't get this number that would make the denominator 0. I didn't, so I'm good. So this is our final answer. All right. Let's see what's next. Okay, actually this one is very similar to the one we just did. So I'm going to skip this one and let you guys do that one at home. I'm going to move on to this one. So this one's a little different than the ones we've done up to this point, mostly because up to this point we haven't had a variable in the numerator. And now we do. And so that's going to change. It's not going to change the strategy, but it's going to change kind of after we remove the fractions, what comes after that. Okay, so we're going to start the same. What x value would make this denominator 0? That may be harder to see right away, so let's work it out. So if 2x plus 1 were 0, which we don't really want, let's solve it. I can subtract the 1, divide by 2. Okay, so we don't want x to be negative 1/2. We want to watch out for that. All right, this problem is kind of like the first one we did in that we only have one denominator. So by default, that's our least common denominator. So we're going to multiply both sides by 2x plus 1. So let's do that. Okay, on the left, these are going to cancel just like we expected. On the right, we're going to distribute this x. That's going to give us 2x squared plus x. What makes this different is the x squared term, right? We didn't have that before. So the solving strategy to solve when I have an x squared is different than it is when I just have x, right? So when I just have x, I can do what I've done in the last couple examples, get all the x's together, right, and move things around. If I have x squared, I want to think about doing factoring or one of those strategies we've been learning about in Chapter 8. Okay, most of these are factorable. So to solve by factoring, I need to get 0 on one side first. So to do that, I'm going to subtract this 6 over to the right-hand side. Then I'm going to factor. I'm going to use the trial and error method here, but if you'd rather use the AC method, that's totally fine. To get 2x squared, one of my parentheses is going to have a 2x, and one of them is going to have an x. In the back, I need two numbers that multiply to be 6. These numbers by themselves are not going to add up to the middle, which is a 1 here, because this 2 is involved, right? So I think 2 and 3 are going to work for these numbers in the back. 2 times 3 is 6. The way I can make a 1 is if I pair this 2x with a 2 here. That'll make 4x. And 3x, if I subtract them, I'll get the 1 that's in the middle. And it's a positive 1, so I want the 2x times 2 to be positive, and I want the 3 to be negative. Okay, then I'm going to set each part equal to 0. And I'm going to solve from there. So I'm going to add my 3. So I get 3/2, or you could make it 1.5 if you want. And negative 2. All right, and just like we've said in the past, I just need to double check. I did not get negative 1/2. So both of these are valid answers. So this time I get 2 answers. think I have one more for us to try. I'm going to take this away now. Okay, so again, same process. What x value is not going to work? Looks like x cannot be 2, since 2 minus 2 would give us 0. The denominators match here, so we're going to multiply by x minus 2. Same thing here. Okay, we've done that so that we can remove the fractions. Oh, technically I'm supposed to do that here too, sorry. But it doesn't really matter because 0 times anything is still 0, so this is going to stay 0. I'm going to be left with x squared plus x minus 2 minus 4. Oops, I spaced that out, kind of weird. That becomes x squared plus x minus 6. Okay, and just like the last one, I have this x squared term. That's what tells me, hey, I'm going to at least try to solve this by factoring. All right, if I couldn't solve by factoring, I guess I usually use quadratic formula after that. But all of these are going to be factorable for you, so you don't have to work that hard. Okay, so if we want to factor, two numbers that multiply to be 6, that add to be 1, I think 3 and 2 are going to work. It's a positive 1, so I want to have a positive 3 and a negative 2. Then I'm going to set each part equal to 0. Okay, and then again, we have to do a quick check. We can't get 2, right? 2 wouldn't work because if I plugged in 2, I'd basically get undefined minus undefined equals 0. And that doesn't count as an answer. And we got 2. All right, so this does not count. It's not going to work. All right, negative 3 doesn't have that problem. So in this case, we only have one answer. All right, and I always like to point out that all the possibilities could happen, right? You could get 2 working answers, which we've gotten in the last example. You could get just 1 working answer, or there are problems out there where both answers do not work. I don't usually give you those because I feel like that would be kind of like a trick, but it could happen, right? All right, I hope that gives you a good idea of the strategy, right? The kind of the steps that we've taken to solve. Remember, if there's an x squared, when the fractions are gone, you want to try and solve by factoring. Well, good luck practicing this, and we'll see you in the next video.